This is going to be a crash course in Unicode for C++ developers. My name is Steve Downey. I'm a software engineer at Bloomberg. Currently on our system reliability team for the communication channels group. Before that, I worked on the back end of our instant messaging system, and then before that, the back end of our email system, where I was doing a lot of the work to convert our backend to store everything in UTF-8 rather than in whatever encoding happened to have the text encoded in, and uncovered a lot of mistakes and problems in our text handling over all of that period of time. So I'm currently also involved in the ISO C++ standardization process. I'm very active in the text study group 16. If everything goes well in the for C++ 23, it will be my fault that you won't be able to throw poo anymore. We're cleaning up what are allowed Unicode identifiers, or allowed identifiers in C++. So, quick abstract. This talk will give you a crash course so you can understand what code units, code points, grapheme clusters are, how Unicode encodings work, how decode and encode algorithms work, what normalization is for Unicode and what the various forms of normalization are and what they're used for, and what the various Unicode algorithms for text processing are. This will give you the tools to understand how not to break your user's text, or at least not too much or too often. Now, first rule for C++, because C++ is often on the back end, the most important thing is to do no harm. Best text handling is not to. You want to, if you can avoid processing the text, that's the best course. If the goal is just moving data from one place to another, so just move the data. You want to push your error handling to the edge. Often misencoded data, you can repair this on the edges, and that often happens. If you have to put in replacement characters or say we don't understand it, we lost data. Standard U8 strings, not like Python 3 string. U8 string is not smart. It just promises that you're supposed to be able to treat the data in the string as Unicode UTF-8. Python 3 strings promises that the data is well-formed Unicode. We've run into problems in some of our internal APIs where we have a string in the Python APIs and the data is misencoded. It may not be Unicode encoded at all, which means there are problems in retrieving data from a database, for example. Try to avoid that if you can. Okay, basic parts. Characters aren't actually very basic. What the fundamental units of writing are vary considerably from language to language. English is one of the simplest, and we've made it even simpler in the last century. English used to use diacritic marks. Those have mostly fallen out of favor. Some of this due to ASCII itself. Unicode tries to avoid talking about characters, except in the very abstract sense. Characters is defined by Unicode to be the smallest component of written language that has semantic value. refers to the abstract meaning or shape rather than a specific shape. So we're not talking about glyph, although in code tables, we're going to have some representation for it, or you can't understand what anyone's talking about it. The synonym, when it's used by itself in Unicode, it's a synonym for abstract character. It's the basic unit of encoding for the Unicode character encoding. It's also the English name for the ideographic written elements of Chinese origin. All of this is quoting from the Unicode glossary about what an abstract character is. Now, an abstract character is the unit of information used for organizing, control, representation of textual data. It's also not a glyph. So we'll speak of the abstract letter A, capital A, for example, and we then will assign it some meaning based on that, some way of encoding the data so that when we're sending data to and from each other, we agree on what it means. Abstract character is also not a grapheme. It's not a specific visual representation or cluster. Now, code units are the basic, most fundamental part of encoding. And for ASCII, most legacy encodings, a code unit is fixed at 1 byte. Code units are things like car or WCAR-T or an octet on the network or a word. And it's basically what the computer works in at its most basic level. Code units are the unit of data that we're sending around. Unicode, unlike previous systems, defines things in terms of code points and scalar values. And so Unicode assigns each abstract character a code point, which is a number from 0 to hex 10 FFFF. Some code points currently unassigned. Some are guaranteed never to be assigned. In fact, most code points at this point right now are unassigned. There's a range used for encoding values outside the 16-bit range in UTF-16. Scalar values exclude that range. So scalar values are what we consider to be Unicode characters, so to speak. And they're the code points from 0 to D7FF and from E000 up through the top of the range. Those are what code points and scalar values are. We have grapheme clusters and extended grapheme cluster. And grapheme cluster is roughly what most people think of as a letter. And it's a base together with some number of non-space marks, combining diacritics. Extended grapheme clusters may include some spacing marks. And we added extended grapheme clusters because text is a mess and some users treat clusters with spaces in them as unit of text. And text is hard. So some things that are grapheme clusters, G with the diaeresis over it. So we have the G with an umlaut there, or the Devanagari SSI, which is that symbol there. We'll get into a bit more about what are combining marks and non-spacing marks in a bit. Now we need to have some way of encoding the data so that we can actually send it to each other. Now, Unicode standard is a universal character encoding standard for written characters and text. This is how the Unicode standard starts off. Encodings are the abstract notions of character and text are made concrete. And Unicode has defined several over the years with more or less success. UTF-8 is the main one. In the WHAT working group, which defines the web platform, it's known as the encoding. UTF-8 is unreasonably good. It's C-string safe, so UTF-8 encoded text can be passed around through systems that expect C strings, in particular file systems. There's no aliasing. Any particular octet of encoded UTF-8 data is distinct from any other particular octet. We can always tell which kind of thing we're looking at. It's self-syncing. We can always tell where to pick up if we've suddenly dropped into the middle of text. Single errors lose at most one character. It's ASCII compatible. The 7-bit ASCII is the first set of is the same for single byte. Start's easy to find. That is where to pick up encoding or decoding data. There was an original Unicode transform format, UTF-1, the original ISO 10646. It didn't encode 7-bit ASCII directly, but it was originally proposed to solve the file system safety problem. If we want to store UTF-8, or if we want to encode Unicode in the file system, we'd like it not to break file systems. David Prosser from the USL had a proposal which was a bit more complicated. UTF-8 was invented by Ken Thompson, which added the self-sync property over the original proposal from IBM, which didn't have that property. All of these things make UTF-8 the best default choice for encoding Unicode. Mechanism, it's variable width multi-byte encoding, where the first byte encodes the number of bytes used. Works like this. We'll see this table in a lot of places. If the scalar value to be encoded is part of the range from 0 to 7F, which is the 7-bit ASCII range. It's encoded as a single byte with a leading 0 and the rest of those bits. For the range hex 80 through hex 77F, the first byte will start off with 110, and the second byte will start off with bit 01, or excuse me, bits 10, and encodes the first 5 bits and then the second 6 bits. 3-byte ASCII, 3-byte encodings work similarly. The first byte will start with 111 and then 0, which signals how many bytes are in the entire package, and they're laid out similarly. And Unicode is currently, and hopefully forever, limited to the range up to 10 FFFF. UTF-8 can actually be extended to 5 and 6 bytes if we ever needed that. That's it. there are specific bytes that fall out from that definition that we know are well formed, so we can quickly detect errors that may creep in and potentially reject quickly misencoded data. Now, UTF-16 came about. Well, originally there was a form called UCS2 to talk about, but we thought early on that 16 bits were enough for anyone to encode all the text forms. We were wrong. It's still in wide use. Windows and Java both use UTF-16 internally. UTF-16, if the scalar value fits in 16 bits, it's just encoded that way. If it's outside that range, we break it into surrogate pairs, where the surrogate range D8 through DFFFF is used, and that's used to encode the upper planes of Unicode. Should never be a lone code point in the surrogate range, always a pair. There is technically UTF-32. It's very simple, almost never shows up in the wild, but it is often used internally to encode, to represent Unicode code points. We have also UCS2 and UCS4, which are the 2 and 4 byte forms before UTF were generally standardized. UCS4 is essentially the same as UTF-32. UCS2 did not have surrogate pairs. The C++ standard has a normative reference to an ancient version of ISO 10646, just to be able to talk about UCS2, which shows up in how we defined some of the character translation encode decode functions. One thing that shows up occasionally, we have WTF8, the wobbly transformation format. There's WTF16, because JavaScript and Windows file systems don't actually enforce well-formed UTF-16. Lone surrogate values happen because in ancient times, before surrogates were invented, those were just unassigned code points, and people would use them for things. This technically ill-formed UTF-16. WTF, basically encoding WTF-16 into generalized UTF-8. We ignore the requirement that only scalar values can be encoded. So actually well-defined spec, you should not omit it deliberately, but this is how you can understand bad data that is sent to you. Now, once we have data on the wires, we have to do encoding and decoding of that data somehow. We have encoders, decoders. Encoders take text, output octets, and decoders take octets and output text. And by text, I mean in this context, scalar values. UTF-8, the encoding scheme, the bytes are ordered exactly as the form says. Byte 1 of a 4-byte sequence comes first, followed by the second, the third, and the fourth byte. Straightforward, and there's no disagreement about this. For UTF-16, we have to deal with possible big endian versus little endian and byte order marks to describe what order things are in. Byte order mark, we have there's a code point FEFF, which is a valid character code, which is a kind of space, and FFFE, which is not a character. So we can use these to distinguish the order of octets for the 16-bit value. Used to be used to signal Unicode UTF-8, that your UTF-8 file might start off with a byte order mark. This is no longer recommended. It just serves to confuse text processing. Generally, the modern protocols agree with it, either out of band per protocol specification, or specify somehow directly in the protocol what encoding is being used, not trying to signal as part of the payload. So for UTF-16, you could have UTF-16 with byte order mark, or it can be implied, or you might specify that you're sending data in big endian, UTF-16BE, or in UTF-16 little endian, or LE. These all show up in practice, to the extent that UTF-16 is still around as a wire format protocol. If anyone sent UTF-32 around on the wire, you would have little endian and big endian versions and byte order marks. Almost always on the wire at this point, we have UTF-8 as an occasional fallback, UTF-16. We also have legacy encodings, which are basically everything before Unicode. No one's really creating new ones at this point. Most legacy encodings are single bytes. They're simple table driven. So for example, Windows 1252, one of the most common one, the 12.5x series, which are the various other Windows code pages, the ISO 8859 series of encodings, which are used for various European languages, KOI 8R and U for Korean data, EBCDIC used very long time ago. It worked well on Hollerith punch cards and is still used widely on IBM mainframes. There are also still private code pages in use in various systems. In the early days of computing, computers which were not networked and barely needed to communicate with each other would often define the encoding of characters and fonts for their own use. It might include, the various line draw characters or shading characters, for example. Bloomberg used for a very long time and still has a lot of legacy data encoded in a code page that includes all of the common European characters and eliminates all control characters, and also has fractions down to 128ths for printing out bond data. This is not useful for interchange, but it did allow us to do localization within our closed walled garden. We now define everything in terms of Unicode. We have a iconv that is extended to do the conversions back and forth. Now, there are a lot of multi-byte encodings because 256 characters is not enough for many languages. Common ones, GBK, Big 5, ISO 2022 JP, which is still quite common in Japan, as is shift-JIS. These are generally state machines with some sort of shift states, where a character signals that we're moving to a different format and that the bytes following the shift are to be interpreted differently. This generally means that any errors may not be recoverable. It's very easy to lose a shift, and then the following characters will appear to be valid in the encoding otherwise, but are entirely jumbled. It's one of the reasons we have the term mojibak, which means broken characters, because they are so common in Japanese encodings. Transcoding is another common function. This is where we want to connect, start with one character set and move to another character encoding set. Unicode is universal, so we can connect a decoder to an encoder and make a transcoder out of it, pivoting through Unicode code points. In practice, of course, there are common pairs that are short-circuited and will transcode directly from one to another. But ICON has for more than a decade, probably maybe multiple decades, pivoted through Unicode to do its transcoding when you ask it to convert from, say, Windows 1252 to Latin 1. And when the transcoding is not available, you can either have error states indicating that you're unable to, or put in various replacement characters where you need to choose a replacement character from the target code set. Unicode has a box with an X through it that's usually often used for replacement character, or the diamond with the question mark in it. The box with an X is actually used for, I couldn't decode that or represent it. The diamond with the question mark is usually the canonical replacement. Now, normalization. Moving on to the next large section. There's more than one way to write things. Combining characters means that some visual text may have more than one representation. Very often there'll be more than one, there will be pre-combined forms. So there are Unicode characters that are, for example, A with accent grob over it. But there's also the letter A, and there's also an accent grob that can be combined with it. There might be more than one diacritic applied to a character, which means we have to have ordering for it. Still, we want to be able to tell if text is the same or not. So we define canonical equivalence and compatible equivalence. Canonical equivalence means that in the abstract, these two pieces of text are essentially equivalent, where compatible equivalence means some information might be lost. Canonical equivalents are things like A with ring over it, which is Unicode code point C5. There is also the angstrom sign 212B. And there is also the Latin capital letter A with the diacritic combining ring above. We have the angstrom sign encoded separately in Unicode, specified separately, to be able to round trip certain texts through it. There are existing uses where people were making a distinction between these things, wanting to be able to say, oh, that's an angstrom sign versus that is a Latin character or A with a ring above it. There are a few places that Unicode will code these things separately so that we can translate through Unicode without losing any information about the original text. But they are canonically equivalent. Compatible equivalence is a much looser notion. So compatible equivalence, we might have the character fraction, vulgar fraction 1/4, which is going to be compatibly equivalent to the sequence 1/4. A non-breaking space is compatibly equivalent with a regular space character. A superscript 9, compatibly equivalent to just a regular 9. Or similarly for a subscript 9, where that's compatibly equivalent with just regular 9. Fractor black letter H is compatibly equivalent with just an H. So compatible is trying to talk about, these are similar enough that if someone is looking for 1/4, they might be okay if they found 1/4, or searching for H, might want to find the fractor H used in math. The other axis we can do normalization on is whether we're going to have decomposed or composed. Particularly for Latin language, Unicode defines code points for precombined characters, such as the Latin capital letter A with ring above that we mentioned before. So we have a choice as to whether to prefer composed or decomposed code points when we're turning a string into a normal form. Now, most IMEs, most input methods, tend to produce composed characters. It's not universal, but when you select that you want to have an U with umlaut over it, you get just the code point for a U with umlaut over it. So given those, we have 4 possible combinations. We have normalization for D, which is things in canonical form decomposed. Normalization form C, which is canonically decomposed followed by canonical composition. Normalization form KD and FKD, which is compatible decomposition, and normalization form KC, which is compatible decomposition followed by canonical composition. Now, you might be asking why you would use which one of these. Compatible is good for applications like search. people don't know which version of the character that they're thinking of might be the one in text. They would like to find all of those H's, generally speaking, even if it's a specific kind of H, which has some semantic difference. We want canonical for applications that need strong equality. C++ identifier equivalence we're specifying to be NFC. We need to specify this because we want to be able to say, tell the linker we're promising the linker is not going to understand text. The linker is looking at octets. So we say that we want identifiers in NFC forms so that when the linker matches them up, it just has to look at the octets. We're agreeing on NFC because NFC is reasonably compact. Now, decomposed is useful because it makes it easier to find base characters, ignoring diacritics. Typically used for things like search on a web page. You're searching for letter A, you probably want to find that even though there might be an A with an umlaut or an A with an accent grave over it. And this extends out to words. We can decompose the text, filter out all the combining characters, and run fairly quick searches for words that are roughly equivalent from a user's point of view, even though they agree that those spellings of those are incorrect without the accents. Now, all normalization risks some loss of information. NFC is generally least risky. That information being there, someone may consider the exact order of combining characters to be important for their purposes. NFC generally preserves the most information, though, by putting things in a strong canonical order. The W3C has some very pragmatic recommendations about how to use various forms of Unicode normalization. It's useful to go take a look at theirs, since they're in the business of interop. Having some advice from them is quite useful. Okay, I'm going to summarize the algorithm. We want to fully decompose. We use canonical decomposition for the C forms, compatible decomposition for the K forms. For each, the order of decomposed code points is defined. That comes from the Unicode database. Combining characters are reordered according to rules. It's like there is basically each combining character has a index for where it goes relative to other combining characters. So there, everyone will agree on a particular format. For NFD or NFKD, we're done at that point. For the composed forms, we recompose the decomposition that we just did with the canonical composition algorithm, which is essentially we go through and replace pairs that have a canonical composition with that composite. So we'll take the lowercase letter A and the combining umlaut, combining diaresis, and replace it with the precomposed character. Now, testing normalization, it's much faster to test if a string is normalized than to actually do the normalization. For every code point, the Unicode database has a property quick check for each normalization form, where basically for each one, we can say the code point cannot occur in that normalization form, in which case you know that your string's not normalized. It might be yes, code point's a starter and can occur in any normalization form. And for NFKC and NFC, the character may compose with a following character, but it never composes with the previous character. Then there's a fairly small set that are maybes. Basically, that text may not be specified in normalization form, depending on the context in which the character occurs. The algorithm is fairly simple. However, it does rely on a lot of data. Basically, we run through the source code, the source text. We check the canonical class of the code point. We check that the class is ordered with respect to what the prior one was. If it's disordered, we can return no. If we check if it's allowed. If the check's no, we return no. If the check's maybe, we result maybe, and then we just iterate through. Get canonical class and is allowed are just looking up data, looking at properties in the Unicode database. Is allowed checks the derived normalization properties for the normalization form we're checking. Get canonical class gets the combining class, which is an ordered enum of how characters combine. Now, there's also a stream safe text format. Because full normalization has some pathologies. You might have very long look ahead, where you actually end up potentially needing n square reads because you have to go all the way to a very long end, then come back and order something, and then you have to start again. For example, if we had a digit followed by 10,000 umlauts, followed by one dot below. The dot below is supposed to be ordered before the umlauts, but that might not be available in your 4K IO buffer. So there is a stream safe format where there is going to be no more than 30 characters that have to be examined. And we use a combining grapheme joiner to mark the boundaries between each of these chunks. 30 characters is, in real text, far more than enough. This is the sort of thing that only shows up in Zalgo text, where someone has deliberately put in horrible, horrible text in order to break your system. Now, let's talk about the Unicode character database. Now, Unicode's much more than just the definition of characters and the encodings. There's a lot of semantics and properties associated with their characters, and those are cataloged in the UCD, the Unicode Character Database. And it's a collection of data files that have the code points, their names, simple and derived properties of those defined characters. Derived properties are based on other properties by some rule. However, stability and correctness concerns means that the derived properties are also usually spelled out quite literally in tables. UCD files, there's a well-defined, you can go to unicode.org, look at their latest database, a bunch of text files that are intended to be machine processable, and also XML files that have equivalent information. The XML files are produced from the machine processable text files. Text files are human readable, but the layouts are fairly straightforward. One of the main files is called Unicode data.txt. The data in it is name, general category, its canonical combining class, the bidirectional class, some things called the decomposition type and decomposition mapping, numeric type and value for numbers, whether it's bidirectional mirrored, Unicode one name, which is now obsolete, comments that were included in ISO 10646, which are also obsolete and deprecated, simple uppercase mapping, a simple lowercase mapping, a simple title case mapping. So an example of that pulled from Unicode data.txt. We have the code point 0041, which is Latin capital A. Its general class is LU. A uppercase letter. We have, and it's case mapping, it's like lower casing maps to 0061. As you see here is Latin small letter or A, class LL, which are lowercase letters. Lower casing small letter A maps to itself. We have a combined form, Latin capital letter A with grave, or Latin capital letter A with acute, both uppercase letter. It's originally had the ISO comment Latin capital letter A grave. When it's case folded, it maps to the Latin small letter A with grave. Each of those, which maps back to C0 under both uppercasing and title casing. As you can see here, the basic format is that semicolon delimit all of the data that's defined for the type for the file. Simply omit things that don't apply to that or don't have a property defined for that. It's fairly easy to whip up some Python to process the Unicode data into something actually useful. Now, looking at some other things, we have for some digits, digit 0, the code point 30, and we can see that those are have values in the digit information where digit 0 has the value 0, digit 1 has the value 1. Superscript 2 has the also has the values 2. Superscript 3 has the value 3. It has the property super, where it's B2. The superscript 2 is super of code point 32. We also define digits in other languages. We have code point 660, where we have Arabic digit 0, which has the same numeric values, 0, as do Arabic digit 1 and Arabic digit 2. So we can use we could use these in interpreting numeric data in text, just as we do for ASCII data. Generally, the digits have the same useful property as ASCII, that they are laid out in a block, so that the code point of 3 is the code point of 0 in that range plus 3. This makes it straightforward to convert to text an integer or floating point. Another example of digit, segmented digit 0 and segmented digit 1. There are Unicode code points that look like old LED clocks. So you have that segmented 0 or segmented 1 looking thing. These look just like zeros and ones, but we indicate that they're used as fonts to supply additional information about what digits are supposed to look like. Now, another important part of the Unicode database, we have derived core properties.txt. In this file, there'll be code points or code point ranges for a particular property, followed by a comment describing the code points by their general categories, how many there are in the range, and what their names are. So it looks something like this. This is the part of the XID start, where XID start is the extended identifier start characters. So these are things that for computer identifiers are useful to start the identifier. And there's an equivalent, there's another property, XID continue. So we have the derived property XID start, some information about this. Comments start with the hash character. XID start, there's a note here that we should refer to UAX15, Unicode Standard Annex, and some comments about how why these things exist. So looking at this data, we have the range of code points 4.1 through 5A, which are Latin capital letter A through Z. These are all letters, and there are 26 of them, and they all have the property XID start. Then the next set of characters that have XID start, code points 6.1 through 7A, small letter A through Z. Anything that does not have the particular property that's being described in the block is just left out. So some other identifier starts, AA, the feminine ordinal indicator, B5, microsign, BA, masculine ordinal indicator. And incidentally, we have used the XID start and XID continue in addition to the underscore character to define what are redefine for C++23. Fingers crossed, I haven't finally voted on it yet. What are valid identifiers for C++? The current list of valid characters included many characters that were unassigned when C++98 was being defined, as well as some characters that turned out to be poor choices, such as left to right modifiers, which change the direction of text. These are not useful things to have in your identifiers. They just confuse people, possibly breaking your debugger. So we have we're planning to adopt the current Unicode standard for these, getting us out of the business of listing code points that are allowed, and with the goal of allowing full access to written languages in meaningful ways for programmers. So overall, I hope an improvement. I've been the lead author on this for the last few years, trying to get this through the standard. The one downside is that emoji are not part of the defined identifier set. So yes, you won't be able to throw poo, the pile of poo emoji. If someone wants to make them identifiers, please bring a paper to the both to the C++ committee and the Unicode committee. I do want to say though that many of the emoji characters, or what are now known as emoji characters, were already excluded from the C++ identifier character set. Dingbats were never allowed. The male and female symbols were never allowed. This turns out to be important for emojis because many of those characters are used as modifiers in emojis, turning them into, for example, the male and female representations. Now, the Unicode database and the properties in it feed into the various Unicode algorithms. Now, many problems with text handling have standardized imperfect solutions. You want to be aware of these algorithms because if you try and do them on your own, you are very likely to end up coming up with something that is worse and doesn't work for some of your user base in ways that they're going to be unhappy with. One of the key algorithms is the bidirectional algorithm. Some text is written right to left. However, in these scripts, digits still tend to be laid out left to right. And we also have a lot of mixed language text. English text will be quoted directly in Hebrew writing. And those quotes will be laid out in their internal order generally. The BiDi algorithm describes how to break apart and format mixed or bidirectional text. At a very high level, we break things into paragraphs, which are the units we would be working with. We identify the character types and their embedding. By character types, is this a left to right character, right to left character, and are we in a left to right context or a right to left context? And you might have a left to right context inside a right to left context inside a left to right context. The algorithm deals with all of this recursively. We resolve the embedding levels, so we can say that we want the right to left text to be laid out right to left, and that should come before or after other left to right text. And then we reorder the lines of text so that you can put them together either by default, how the algorithm specifies, or there are Unicode code points that provide more control over how text should be laid out. I alluded to that earlier with the left to right modifier. Essentially, you can put a code point in that says, whatever you would do generally, just go ahead and put this text in right to left. These things are often used to humorous effect on Twitter or an email. It's like putting text backwards. Other important cases for dealing with bidirectional text, text selection. If you have mixed text, where does your cursor go as you arrow through the text? If you're selecting a whole sentence, what gets highlighted and how does that highlight get broken up? The Unicode algorithms help answer these questions so that users have minimal surprise and as least upset as they can. For many issues with text, there are no perfect answers. They're not even necessarily good answers. There are acceptable conventional answers, though. And one of the goals of specifying all this is to have expectations around what are the conventional answers that computers can then do, so as not to have all of our users up in arms all the time. Another important algorithm, line breaking, aka word wrapping. Putting out text on a page or on a screen, we want to wrap at word points, not just in the middle of a word. Unless you're a programmer, then we may be fine with that. We are poor users of our own tools often. The line breaking algorithm produces a list of break opportunities for a given text. We classify characters as mandatory breaks, an optional break before, optional break after, prohibiting breaks, or kinds of breaks that we want a vertical break or horizontal. And also characters that must not be broken. Only surprising things is how many reasonable ways and places there are to separate lines. Unicode report TR14 outlines how to do all of this. So examples of mandatory breaks, the actual new line characters, or the new line sequence that's used on whatever the convention is for your operating system, CRLF, LFCR, etc. Optional break before, space characters are often disallowed as an optional break before. You don't want to break before a space. You want to break after the space, and then probably elide the white space when you're doing the actual layout. There are optional hyphen characters often, where this is a point where you might break the text, indicating where it's indicated in the text. There are places where we do not want to break at all between these two kinds of symbols because that confuses the meaning of them. And having someone else having gone through and worked out all of the ways that these pairs of things can be put together means you don't have to be terribly inventive. Now, another key set of algorithms is text segmentation. Basically, how do we separate text into significant user-perceived elements? We have user-perceived characters, grapheme clusters or extended grapheme clusters, words, or sentences. The default algorithms also provide tailoring points because often we need dictionary information to be able to understand whether a character is used in isolation or it is and should be considered a character, or really it needs to be combined in this case with the following or preceding character code point. There is a lot of reuse of scripts throughout the world where even though they are using the same script, the same font, they have languages may have different rules or expectations about how things are broken into chunks. TR29 describes all of this. So the grapheme cluster boundaries, these are user-perceived characters. The default units for a grapheme cluster is a default unit for words and sentence boundaries, and also they're relevant for the line break algorithms. Now, grapheme clusters can be detected by Unicode regular expressions that are fairly straightforward to generate. Your typical regex engine, unfortunately, does not understand Unicode regular expressions. But still, we can build a fairly straightforward state machine to process them given the various classifications of text. At least when someone's gone through all the classification work. It's generating these Unicode regular expressions is less straightforward for words and sentences, but it is possible. The ICU software, the open source Unicode text processing APIs has Unicode regular expressions for all of these things, which makes their algorithms quite efficient. Unicode regular expressions allow you to query the Unicode database, so you can say all characters that match a particular property from the Unicode database, such as is combining character or is XID start, to use a property that I mentioned earlier. Now, once we have grapheme clusters identified, we might look at word boundaries. Taking this example from the Unicode standard for breaking algorithms. So we have the quick open paren, quote, brown, close paren, close quote, close paren, fox can't jump 32.3 feet, comma, right? So the search term brown, if we were looking for words, would match. Brown is a word in this context. Brow, if we were searching for this, would not match as being a word. Because we have an N immediately following it, and N is a letter, so brow is not a distinct word. However, brown in quotes, we would want to match because that's our expectation of a possible word. And in fact, the brown in quotes in parentheses would be found by the Unicode word finding algorithm. And in fact, if we searched for the brown in quotes in parentheses with spaces around it, we would say, okay, yes, that's also could count as a word. You asked me for spaces, I will treat them treat that as a word. Word boundaries are, of course, then useful for figuring out sentences. Now, sentences are actually fairly complicated because text can embed itself, and that makes it difficult to analyze. So we have, so for example, the sentence, "Is this a sentence?" question mark, end quote, Steve asked. There are patterns, though, that people will accept as reasonable. So the sentence inside the quotes is a reasonable sentence. However, since it has a ending punctuation inside the quote followed by a space, the sentence boundary for this would end after the period. These things aren't perfect, but people generally agree on what that the answers are good enough for being able to work with text, at least in an automated fashion. Unicode database provides properties that classify characters as likely sentence breaks and defines likely sentences by pairs of characters with those properties. So period followed by a space or an end of line is a very likely a sentence boundary, whereas quote quote followed by a letter is not, or what would otherwise be a sentence ending punctuation mark followed by a quote is likely not a sentence ending. However, if the quote, if you instead had question mark, quote, new line, well, quote, new line is likely a sentence ending mark, so that that would get identified as a sentence breaking point. Okay, now let's talk about a little bit of the future, for past and future for C++. What have we been doing for C++ in order to make Unicode much more useful for C++ Unicode? In C++ 20, we added car 8t to go together with car 16t and car 32t. We've also specified, although everyone was doing this anyway, that car 8t always means UTF-8, car 16t means UTF-16, car 32t means UTF-32. So each of these character types has a well-defined associated encoding. One of the other things that we've been working on is cleaning up the standardized language for discussing things like encoding. Car by itself does not have a well-defined associated encoding. Current locale may imply one, but doesn't strictly define it. In fact, if you're dealing with text in coming from multiple sources, you may have multiple encodings in play in your car or unsigned car types or signed car. This is, of course, a great challenge. And locale does not help a lot in this arena. For C++ 23, we're on track to adopt Unicode identifiers, cleaning up what can be used. This is particularly useful since GCC has recently cleaned up their long-standing bug for not handling UTF-8 source code. So now GCC will let you encode your source in UTF-8, so you can use all these wonderful identifiers. Please discuss with your team before you do this. The C++ standard will limit to a well-defined set, but it's entirely reasonable for style guides to suggest perhaps you should not use Cyrillic I and lower Latin I in the same block of code, since they're going to look the same. We're also cleaning up what we mean by literal encoding. It turns out, to the surprise of many people, execution encoding isn't actually a phrase in the standard at all. There is an execution character set, but it's very complicated what it means. What we can agree on is that literals have some fixed encoding that the compiler determines when it's compiling string literals or character literals. We're defining the term for this to be the literal encoding. We're also proposing to somehow make what encoding was used available to the program. We're also doing a lot of work on defining what portable source code is, that we want to require compilers to accept UTF-8 encoded source code, have well-defined whitespace handling. What is the significance of whitespace at end of lines? There's disagreement on this. We'd like to clean this up so that we can make sure that your source code can be compiled identically among any conforming C++23 compiler. Now, the next bits of things have asterisks by them because the future is uncertain. We'd like to for C++23, and it is still just barely possible. For those of you not involved in the C++ committee, C++23 is frighteningly close from a standardization point of view. The window will probably, for anything new, is likely to close at roughly the end of this year, giving us just enough time to clean it up and make sure we haven't broken anything next year before it's released in 23. What we'd like to be able to get in is to have encoding and decoding ranges, essentially being able to take those octets coming in off the wire and encode or decode into whatever encoding forms that the compiler understands. We will probably require UTF-8, 16, 32, as well as an encoder for WCAR-T, and if we can sort out the good mechanics for it, for whatever the literal encoding was, so that you can translate your literal encoding to Unicode. We would also like a more, and this is a stretch goal, a strong type for text, something that is a container that allows you to do things like take 2 bits of text and concatenate them and still have the text be well-formed Unicode, do strong normalization, be able to search within it, to be able to do the various normalization forms coming in and out of it, while it ensures maintaining the invariant that the text is well-formed for whatever forms of well-formedness we're requiring. For C++ 26, we'll probably be adding more text with more, since it's very likely that that's going to slip. And for C++ 26, provide range-based algorithms for the Unicode algorithms that we were talking about before. Help is very much welcome for all of this. Okay, I guess we'll close this up now. Thank you all for coming. Had a lot of fun putting this together. And see you all in the virtual gathering space. That's it. Bye-bye, everyone.